Hello, everyone, and welcome back to Met Zone African Motives. So, I want us to continue from where we left. We are looking into grade 10 physical sciences for term 1, and now we're now looking into longitudinal waves. And we say that examples of longitudinal waves, they include sound waves. And this is the topic that we want to dive deep into now. Now, before we can start looking into sound waves, I want us to start by looking into how longitudinal waves actually travel. So you would see that what we refer to as longitudinal waves, we say that they travel the particles of the medium, they actually get to move what? Parallel to the what? To the wave motion. Now we want to see how they actually propagate. So we are saying that a vibration starts at one point and then it pushes nearby particles forward. So you would get to see that, let's say, for example, these are particles of the medium. So a vibration starts on this particle and then it gets to push the next particle, and then the next particle also gets to what? To push the next particle as we go. But however, also this particle would push back. So you would see that the first particle moves forward and then backward. Whilst now, when it is now moving backwards, the second particle also what? Moves forward. And then the third particle, the fourth particle. That is how the longitudinal waves, they are actually what? They are actually transferred, or else that is how they travel. We are simply saying that those particles, they get to push the next ones and energy moves forward through the medium. So we are saying this is our spring. So from our spring, this first this first sling of the spring actually gets to stretches and then it bounces on the next goes and goes and goes and goes. That is how the particle would be moving. From one particle, it pushes the nearby pushes the nearby, and the nearby pushes the neighbors. And then now we are saying that these particles, they get to push the next ones as we go. And that is how energy is simply transferred. So the medium itself, it stays in one place. Like I've said that if we were having particles like this particle actually gets to vibrate forward and then it pushes the next particle to vibrate forward. But however, this particle would also get to what? To vibrate backward, because its motion, it's back and forth. So it will remain where it is. So by the end of the disturbance, these particles, they just remain where they are. That is why we are saying that the medium itself, it stays in one place. So we are saying that the properties of longitudinal waves, they require a medium to travel. They either require solid particles or else liquid particles or else a gas. If there is no medium, they cannot travel, because we need to pass through the vibration from one particle to another. So if there are no particles, then there won't be any what? There won't be any movement within this medium. So we are saying our energy won't be transferred from one particle to another. Hence, therefore, there is no wave. So there is only transfer of energy, not of matter. Matter stays in one place. And then we are saying the speed of longitudinal waves, they depend on the properties of the medium. What do we mean by that? We are saying that longitudinal waves, they move faster or else fastest in solid, and then faster in liquid, and then slower in gases. So when you have got solid particles, you know that the longitudinal waves would move fastest. And then it would also get to move faster in liquid and then slower in gases. Now, since we now know and understand how longitudinal waves actually propagate, or how they actually get to travel, let's now dive deep into sound waves. because sound waves are one important examples of longitudinal waves that apply in our daily lives. We make use of some sound properties to actually get to what? To use a different, or else let's get to say, in our daily life, we apply different properties of sound waves. Like for example, sonar, which is applied in submarines, it calculates the depth of the sea. And then we go to sonography, where if you want to go and scan your body organs, you can go through a sonograph. So these are one of the most important examples of longitudinal waves that apply in our daily lives. That is the reason why we dive more deep into sound waves, because they've got what? They've got practical applications in our lives. Now, what is it that we refer to as sound waves? Sound waves are just pressure waves that are produced by vibrating objects. Like if you pull a string and then you release it, that string will vibrate. The vibrations that come from a string, I'm sure you can actually get to hear some sound. So that is what we refer to as sound. We are saying these are just pressure waves that are produced by what? By vibrating objects. For example, take a guitar string, it vibrates. That means that the guitar strings, they get to push air particles forward and backward, creating a sound wave that travels to your ears. Just like, for example, here, we are saying we have got a sound source, which is your guitar. When you pull that string would vibrate, which pushes the air particles. And then these air particles, they actually get to push each other, transferring the energy that they received from the what? From the guitar string. So that energy is what you hear in your ears as sound. So you would see that we have got what? We have got denser spaces and what? We have got sparse spaces within the air particles. That is what we refer to as rarefactions and compressions. And through these, that is how our sound propagates. So what we simply refer to as sound waves, these are pressure waves that are produced by vibrating objects like a string, which gets to push our air particles forward, that is transferring the energy within the medium. So that energy is the one that is being transferred, is the one that is moving within our medium. That is the one that we get to sense in our ear is sound. Now, how our sound travels, it differs with what? With the medium type, or else with the type of medium. Like for example, in our solid, in our liquid, and in our gases. We know that our solid has got its particles closely packed together. The particles here are closely what? Pegged together. And then in our liquid, our particles, they are relaxedly pegged. They've got some small spaces within them. That's the reason why they are able to slide past each other. But when it comes to gas particles, these are actually what? Randomly pegged. They are sparsely specked. Meaning to say that we actually have particles that are actually what? They are spread out. The particles of the gas, they are actually spread out. So you would see that sound would actually get to have different speeds in different what? Type of packing. So where you have got solid, where the particles are closely packed together, you will see your sound moving or traveling faster. So sound travels fastest in solids. Why? Because the particles in solids are closer together and they pass vibration energy more quick. But when it comes to liquids and gases, the particles, they are sparsely pegged, or else they are spread out. So the transfer of what? Of this vibrational energy, it actually moves slower. That's the reason why we would have our sound traveling what? fastest in solids and slower in liquids, as well as slowest in gases. So this is the depiction, or else these are pictures that shows you how our sound travels in different what? In different mediums. So I just took these pictures from the internet. I wanted them to save us in giving us a picture or else an image of how our sound actually travels in different mediums. So this is the picture or else the depiction of how our sound travels. It just shows us how fast in the solid particles our sound would actually get to travel, and how slowly the sound particles or else the sound would actually get to travel in the what? In the gas medium. So we have said that this speed of longitudinal waves depends on the what? On the properties of the medium. That's the same with sound. So sound would travel faster in solids. It will later travel slower in liquids and slowest in gases. Now we want to look into properties of the sound itself. So I'm sure you have heard people referring to sound as of high pitch or else of low pitch. And sometimes it is confusing. You think what they refer to as pitch is what they refer to as what? As the loudness of the sound. These two, they are different. We have what we refer to as the what? As the pitch of sound, and what we refer to as the loudness of sound. So pitch depends on the frequency of sound. The higher the frequency, which means that the greater the number of waves that are passing through per unit seconds, the higher the pitch. So the higher the frequency, the higher the pitch. Like for example, if you whistle, or else if you use that whistle that you have heard, let's say for those who watch soccer or else any games, there is a whistle that they use to either signal the starting of the game or else the end of the game. And I'm sure you've heard that the pitch of that whistle is high. You can hear it from afar because each piece, because its pitch is actually piercing. So we are saying that the pitch of sound depends on the frequency of that sound. So the higher the frequency, the higher the pitch. So when you are given two different graphs like this, just know that this resembles what? A higher pitch, a high pitch. It resembles a higher pitch, where we are saying that there is higher frequency. And then this one, it resembles what? Lower pitch, where we have got what? Lower frequency. At some point in time, they might use the wavelength to describe the pitch. So just know that the wavelength becomes the opposite of what? Of frequency. The higher the frequency, the what? The smaller the wavelength. So when you have got a higher frequency, you have got what? You have got a longer wavelength. When you have got a higher frequency, you have got shorter wavelength. You have got shorter wavelength. You have shorter wavelength. When you have got low frequency, you have got what? Longer wavelength. Which simply means that when you have got shorter wavelength, you have got a higher pitch. When you have got longer wavelength, you have got lower pitch. That is how you differentiate pitch of sound. And then now, let's look into the loudness of sound. How do we determine the loudness of sound? So loudness depends on the amplitude of the sound, which means that the bigger the amplitude, the louder the sound. The bigger the amplitude, the louder the sound. And then the lower the amplitude, the quieter the sound, or else the softer the sound. So loudness moves hand in hand with what? With softness. So we know that a soft sound has got a lower amplitude, or else a quieter sound has got a what? It has got a lower amplitude. And people, they've been using the word of increasing and lowering the volume when they want to increase the what? The loudness of the sound. So you would know that a higher volume corresponds to louder sound. So it will correspond to what? To bigger amplitude. And then lower volume, it corresponds to what? To soft sound, which corresponds to smaller amplitude. So that is how we determine the what? The characteristics of our sound. Those are the properties of sound, where you would know that a louder sound is coming from a higher amplitude, and a softer sound is coming from a what? A smaller amplitude. A higher pitch sound is coming from a higher frequency. A lower pitch sound is coming from a lower frequency. You need to remember that. And then we actually have different ranges of sound. Some of the ranges of sound, when it comes to human ear, it is actually negligible, or else you won't hear it. For example, humans, they only start hearing sound when it has got a frequency of what? Of 20 hertz. Anything less than 20 hertz, we call it infrasonic, meaning to say that we can barely hear it. With our ears, we cannot hear that sound. Meaning to say that a sound that is coming from, let's say, 1,000 miles, you can barely hear it. That means that that sound, it is a frequency of what? Of lower than what? Lower than 20 hertz. But when you go to things like your dolphins as well as your elephants, these are very, very sensitive to lower sound frequency. Like, for example, a dolphin can actually get to hear a sound that is coming from 1,000 miles. It can actually get to hear a submarine coming from 1,000 miles. This helps animals like dolphins to actually get to navigate into safer what? Into safer environments. And then when it comes to humans again, we have got higher frequency that are damaging to our ears. Like, for example, a frequency that is greater than 20,000 hertz, we refer to that sound as what? As ultrasonic. Ultrasonic are damaging to our ears. Ultrasonic, they are damaging to human ears. Like, for example, when they want to torture you, they can use a sound that is having a frequency that is higher than 20,000 hertz. That sound can actually get to make your ears start to bleed. So, at some other instances, they will ask, what is a sound that you refer to as ultrasonic? Ultrasonic sounds are sounds that are having frequencies that are greater than what? 20,000 hertz. That is the last number of sound that we can actually get to tolerate in our ears as humans. But you would also get to see that from this table that I've brought you here, dogs can actually get to hear a frequency that is actually greater than 45,000. They can tolerate that kind of sound. And then when it comes to dolphins as well, they can tolerate a sound that is greater than 200,000. Meaning to say that when submarines are navigating closer or else near dolphins, they can actually get to what? They can actually get to tolerate those sounds without having their ears being damaged, or any sound that is having a higher frequency, they can tolerate. But when it comes to elephants, yes, they can hear lower frequency sound, but anything that is above 10,000, that is very damaging to it. That's why people who live nearby, maybe let's say game reserves, where elephants, they actually get to move around. When they want to scare away elephants, they use things like drums. Let's say metal drums. They start ringing or else playing those metal drums. What happens to elephants is that that sound, it is actually damaging to its ears. So that is how they manage to scare away elephants. So this table shows us different ranges of what? Of sound that is tolerated by different types of animals. For humans, our lower frequency is 20 hertz. Our upper frequency is 20,000 hertz. For dogs, we have got 50 and 45,000. For cats, it's also 45 and 85,000. And then for birds, it's 20 and 120,000. For dolphins, that is the most sensitive one. It can hear sounds of far much more less than one frequency, which is just 0.25 hertz. And then it can also get to withstand sounds that are coming from a source that is releasing a frequency of 200,000. And then for elephants, we've got 5 and 10,000. Now, we have something that we refer to as a sound reflection. We have something that we refer to as sound reflection, which is one of the most useful property of what? Of sound waves. Now, what is reflection of sound waves? Reflection of sound waves occurs whenever sound waves, they bounce off a surface and then they travel back to the listener instead of being absorbed or transmitted through the surface. So this is when, let's say you are in a room and then you speak, and that room, let's say it's big enough and it is empty. You speak, and then after some time, you hear somewhat. You hear some echoes of your what? Of your voice. That is what we refer to as a reflection. So in actual essence, the specific sound reflection within a short time delay is what we refer to as an echo. So an echo is a reflected sound that is heard after a short delay or else a short period of time from when the original sound was produced. So we use this property of sound in our daily lives. For example, when it comes to sonography, or else when it comes to what? To sonar in our submarines. So let's look into the uses of what? Of ultrasound reflection and echoes. So the other uses of ultrasound reflection and echoes is what we refer to as what? As measuring distances. We can use ultrasound reflection as well as echoes to measure the distance. E.g., when we are in our submarines, we can use the reflection of ultrasound or else of sonar to measure the depth of our what? Of our ocean. Because we are saying that the sound waves that we get to what? To release into our ocean, we know their properties, like we know the speed of sound. The speed of sound is usually what? 340 meters per second. The approximate speed of sound is usually 340 meters per sound. So through the reflection of these sound waves, when we emit sound waves in the ocean through a sonar or else a sonar detection unit, we'll be knowing its speed. And then we measure the time it is reflected back. That time would actually get to tell us how deep the ocean is. By just knowing that the time taken to get our reflection, it resembles twice the time it takes to go down to the depth of what? Of our ocean. So half of this time gives us the time it took our sound wave to travel down the what? Down the depth of our ocean. So we can use now distance and the time period to calculate the distance from our ship to the depth of the what? Of our ocean. And then when it comes to medical medical uses and application, we have what we refer to as medical imaging. We use ultrasound for what we refer to as what? Ultrasound scanning, which we refer to as sonography. For example, when we want to monitor or else to check our human organs, like for example, the liver, we want to see how damaged it is or else how healthy it is, our kidneys as well. So checking the normal liver or else how fat a liver can be, we can actually get to use what? Ultrasound, which we refer to as ultrasound scanning. Or else we can also use sonography for monitoring the heartbeat of unborn babies. We can also use ultrasound and echoes to actually get to detect the speed of what? Of objects. Like for example, the radar, we use radars as well as sonar systems in either in our ships or else when it comes to our aeroplanes. We can use what? We can use these echoes to actually determine and detect our speed and objects in air. And then we have animals like bats as well as dolphins. They use echoes to maneuver or else for navigation. Our bats, they do not have our vision that we have. Like they do not see the way we see, as well as dolphins. Their vision is very poor, but they use sound to navigate. So how do they use sound? They use what we call echolocation to detect prey and obstacles. When they are navigating, they use this sound reflection to detect what? Whether there are objects around or else there is prey around. So these are the uses of what? Of ultrasound reflection and what? And echoes, which you are required to know. At some point in time, they will ask you, give us examples of the uses of ultrasound or else of what? Of echoes. So before we can conclude our class, I brought you a question paper or else a question from a certain question paper. This was a November question paper, which was written in 2024 in the Eastern Cape. So this was for what? For our November 2024 from the Eastern Cape. So now let's see what is it that they were asking in terms of what? In terms of sound waves, so that we know and at least have an idea how they will be asking us and what exactly they would need us to know. So here question number 2.3 was saying, a sound wave moves along a slinky spring. Position A is given from the diagram, and B are the centers of a compression and a rarefaction respectively. So A and B are 24 centimeters apart. So here, this is the center of a compression. This is the center of a rarefaction. And we can see that we also have another compression here, another compression there. So you can actually get to see that here I've got a wavelength. And then here I also have got another wavelength. But here I've got what? Half of a wavelength. So I have got 2.5 wavelengths, which is 5/2 of my wavelength from A to B. And they are saying this is equivalent to what? To 24 centimeters. Okay, that is fine. Let's now look into whatsoever that they want us to what? To calculate there. We now have an idea of what is happening. Question number 2.31 is saying, are A and B points in phase? Write down your answer as yes or no. These 2 points, they are not in phase. No, they are not in what? In phase. Why? Because this is a compression and this is a rarefaction. Only compressions and compressions are in phase, and only rarefactions and rarefactions are in phase. So you would say, no, these 2 points are not in phase. And then they're saying, give a reason for your answer. You would say A is a compression and B is a ray refraction. By stating that, by just stating that this one is a compression and this one is a ray refraction, we actually understand that point A and point B, they are not what? They are not in phase. Now, let's look at question number 2.32. It is saying, determine the period of the wave if it takes 5 seconds for a particle to move from A to B. What becomes the period of the wave to move from A to B? So we know that the period determines the time it takes to move one wavelength. Time to move one wavelength. So we need to know how many wavelengths we have between A and B. We said we have 2.5 wavelength. So if we have 2.5 wavelength, that is to say that we have got what? 5/2 wavelength. And the time taken to cover 5/2 wavelength is 5 seconds. What would be the time taken to cover one wavelength? We can simply say 5 seconds divided by what? By 5/2. That is 5 seconds divided by 2.5. Because here we have got 2.5 wavelength, which is equal to 5 seconds. What would be the time taken to cover one wavelength? That is what we are looking for. So let me just get to wrap through here because we now know this. So we know that period is the time taken. So your period is the time taken to cover what? One wavelength. Time to cover one wavelength. So we are saying that we have got 2.5 wavelength being equal to 5 seconds. They are covered in 5 seconds. What about one wavelength? It will be equal to what? So one wavelength will be covered in 5 over what? 2.5. So that we can actually get to know that our time period would be equal to 5 over 2.5, which is just equal to what? To 0.5 seconds. So the time taken to cover one wavelength was going to be equal to what? 0.5 seconds. So please, guys, use your calculators to just say 5 divided by 2.5. You get what? You are going to get 2 as case there. You are supposed to get 2, not 0.5. You are supposed to get 2. So the answer here is supposed to be 2 seconds. Supposed to be 2 seconds. That is the time period there. If that is the case, now we are saying a note on this sound wave with the same speed that is given above is played at a higher pitch than before. How does this affect the following? How does this affect the following? If we are now playing the same note of the sound at a higher pitch, how will it affect the amplitude? Amplitude is only affected by the loudness. So this won't affect the amplitude. So you would get to say what? Remains the same. Pitch does not affect amplitude. We said pitch affects what? Frequency. So pitch affects frequency and amplitude is affected by what? We said amplitude is affected by the what? By the volume or else the loudness of sound. Now, they are saying that if we are to play at a higher pitch, the distance between A and B, the distance between A and B resembles the number of wavelengths. So this is going to decrease because we said, remember, we said a higher pitch, it will have a what? A higher frequency. And we know that a higher frequency will have a what? A shorter wavelength, which is a shorter distance moved. This is the shorter distance moved between what? Two compressions. So the distance here has to be shorter when we are now using a what? A higher pitch. When we use a higher pitch, the distance is going to what? Is going to decrease. And then what about the period of the wave? Now the period of the wave is also going to what? To decrease. The time taken to cover the what? One wavelength. The time taken to cover one wavelength. What is going to happen? We know that our frequency is equal to 1 over t. So if our frequency is going to increase, it simply means that our time period has to decrease, because these two, they are inversely proportional. So this one is also going to what? To decrease, because our frequency is going to increase. So that is what they expected you to do there on question number what? Question number 2.3. And that is how they would expect you to answer questions to do with sound waves. That is what you would be expected to know. So thank you so much, guys, for being together. Let's meet in our next videos to come. We are now diving deep into electromagnetic waves.